In this class, we are going to discuss about the growth and decay of current in a series LCR circuit. Okay, we know in a circuit consists of inductor or capacitor. The current or charge in the circuit does not attain the final maximum value instantaneously after the connection of the steady state voltage source. Okay, circuit takes some time to reach the final maximum value. Again, if we disconnect the circuit, the current or charge in the circuit does not fall to zero immediately after disconnection of the voltage source. Okay, thus there is a time interval between switching operation and reaching a final steady state of current or charge, during which current or voltages or charge in the circuit varied. Okay, but the variation of current or charge or voltage in the circuit exists for a very short interval of time. So it is called transient phenomena. Okay, now let's see the circuit diagram. And in the circuit, this is inductor and this is resistance and this is power supply. Okay, connect in a series, and this is switch. If we on the switch, that means short the switch at t is equal to 0, then current start to flow in the circuit. Okay, and let at any instant of time current in the circuit is I, and at that instant the rate of change of current in the circuit is di dt. Okay, then the voltage equation of the circuit can be written as E equal to the voltage drop across resistance is R I plus voltage drop across inductor, and it is L di dt. Okay, so this is the voltage equation of the circuit. Now from this equation we can write L di dt equal to L di dt is equal to E minus Ri. Okay, or di by E minus Ri equal to 1 by L d dt. Okay, if we integrate it, then what we will get? After integration we will get minus 1 by R ln E minus Ri equal to 1 by L t plus integrating constant C. Okay. Now if we use the initial condition, we know and the switch is just closed at that time, that means at t equal to 0, current in the circuit is 0. Okay, no current flowing in the circuit. And if you substitute the values in this equation, then we will get minus 1 by R ln I equal to 0 at t is equal to 0, so this term will be 0, that means E, and also this term will be 0, so this is equal to C. Okay, so this is the value of the integrating constant. If we substitute the value of C in that equation, just in the above equation, then we will get minus 1 by R ln E minus Ri 1 by L T minus 1 by R ln E. Okay. Or if we rearrange the equation, then we will get minus 1 by R ln E minus Ri divided by E. From these two terms, this term and this term. From these two terms, we can write minus 1 by R ln E minus R by E. Okay, using the rules of logs. So this equal to 1 by L T. Okay, or ln E minus Ri by E equal to minus R by L T. Okay, or one minus R by E I equal to minus R by L T, or 1 minus R by E I equal to exponential minus R by L T. Okay, or R by E I equal to 1 minus exponential minus R by L into T, or E equal to E by R 1 minus exponential minus R by L into T. Okay, so this equation represents the growth of the current in the circuit. Okay, I equal to, if we, and the current in the circuit increases exponentially with time, because with increasing of time, here exponential minus R by L is constant. So with increasing t, this term will be reduced. So the negative term reduced means the current is increases. Okay, at t tends to infinity, if we substitute t equal to infinity, then exponential minus infinity. So this exponential minus infinity equal to 0. So E equal to E by R, and this is equal to I0. This is the final steady state value at t equal to infinity. Okay, here L by R has the dimension of time. So it is called time constant. Okay, so it is represented by tau equal to L by R. If we substitute the value of tau in that equation, what will be the value of the current in the circuit at one time constant. So let's see, 1 by r, 1 minus exponential minus r by l, and tau is equal to l by r. Okay, so l by r, and this is equal to e by r, 1 minus, this will be cancelled, so exponential minus, so 1 by e. Okay, and this is equal to I0 into 0.63. Okay, thus the time constant is defined as the time during which the current in the circuit become 63% of its final maximum value. Okay, if we draw the variation of the current with time, then the nature of the graph will be, this is the time and this is the variation of current. Okay, at t is equal to 0, at t is equal to 0, t is equal to 0 means exponential. Let's see the equation. If we substitute t is equal to 0, so exponential 0, exponential 0 equal to 1, so 1 minus 1 equal to 0. So at t is equal to 0, current in the circuit is 0. So the graph will start from the origin and increases exponentially. Okay, exponentially increases the current and become maximum value at steady state, and the value will be I0. I0 means E by R. Okay, and at the steady state value, when the current in the circuit become steady state, then the rate of change of current di dt will be 0. Okay, then no voltage will be dropped across the inductor, then the circuit as if behaves as a the circuit as if behave without inductor. Okay, because then the maximum voltage, total voltage will be dropped across the resistance. The voltage drop across the inductor and resistance at any instant time, the voltage drop across resistance VR equal to, we know the at an instant the equation of the current in the circuit is I, so I into R, and this is equal to R into E by R means I0. Okay, 1 minus exponential minus R by L into T. This is the instantaneous voltage drop across the resistance, and t equal to infinity, at t to infinity this term will be 0, so the voltage drop across the VR equal to Ri0, and the voltage drop across the inductor at any instant of time will be L di dt. Okay, or L, if you differentiate with respect to time, then di dt will be, this will be 0, so E by R into minus here another negative sign, so R by L into exponential minus R by L into T. Okay, or this is equal to, this is I0. Okay, so LL cancelled, so R I0 exponential minus R L by T. So this is the instantaneous voltage drop at any instant of time across the inductor, and from this equation we see that the voltage drop across the inductor is decreases with time, because there is a negative sign. With greater value of t, the value will be smaller. So with increasing of time, the voltage drop across inductor will be reduced, and at t equal to infinity this will be 0. So at t equal to infinity, the voltage drop across the resistance equal to R I 0. At t equal to infinity, this will be 0. So the voltage drop across R I 0, and if we substitute the value of I 0, we know I 0 equal to E by R. So the total voltage will be dropped across the resistance, and voltage drop across the inductor will be 0. Okay. Now I will show you the decay of the now I will show you the variation of the graphical variation of the voltage drop across the resistance and inductors. The x-axis along this represents the time axis with time, and in that axis VR or VL. Okay. At t equal to 0, t is equal to 0 means this term is equal to, so no voltage drop across the resistance. At t is equal to 0, let's see the equation. T equal to 0, this term exponential 0, so 1 minus 1, 0. So no voltage drop across the resistance. So with increasing time, the voltage drop across the resistance increases exponentially. Okay, but if we see the equation of the voltage drop across the inductor, here with increasing of the time, at t equal to 0, t is equal to 0 means this term will be 1. So the at t is equal to 0, total voltage drop across the inductor, that means Ri 0, and this is equal to E. So the at t is equal to 0, maximum voltage across inductor, and with increasing of the time, the voltage decreases exponentially. So these are the variation of the voltage across the resistance and inductor. Okay. Now I will show you the decay of current in the circuit. Let's see the circuit diagram. This is the inductor, and this is resistance, and this is power supply. Okay, this is B, C, this is A point, and this is K switch. During the growth of the current, the A point is connected to the point B. Okay, so the current in the circuit become maximum and reach the steady state value I0 is equal to E by R. Suppose the already reached the steady state current after the close of the switch in the LR circuit. This is L and R. After reaching the steady state value of the current, if we connect the A point to the C point, then current in the circuit start to decay from maximum value I0. Okay. Then in the circuit there is no voltage source, so the voltage equation can be written as, let at any instant of time after connecting the A point to the C, the current in the circuit is I. Okay. So, and rate of decay of current is dt at that instant. Okay. So the voltage equation of the circuit can be written as L di dt. This is the voltage drop across the inductor plus ER is equal to 0. Okay. Or di dt equal to minus R by L I, or di equal to minus R by L dt. If we integrate it, we get ln I is equal to minus R by L t plus C1. This is another integrating constant, and at t equal to 0, at t is equal to 0, the current in the circuit was I0, maximum current. So at t is equal to 0, I is equal to I0. If you substitute the value of I in that equation, then you will get C1 is equal to ln I0. Okay. Now substitute the value of C1 in that equation, then we can write I by I0 is equal to minus R by L into t. Okay. Or I by I0 is equal to exponential minus R by L into t. Or I equal to I0 exponential minus. Okay. This equation represents the decay of the current in series LR circuit. Okay. And the variation of the decay of current with time, this is the time axis and this is the current axis. At t is equal to 0, the current in the circuit was maximum and the value is I0. If we substitute the t is equal to 0 in that equation, then it will be 1. So the maximum current, and with increasing of the time, the current decay exponentially. Okay. And here R by L represent L by R represent the time constant for the decaying of the current, and if we substitute the value of t equal to L by R, that means the time constant, what will be the current after one time constant? I equal to 1 by A, and this is equal to 3.7 into I0. Thus the time constant for decaying of current is represent the time during which the current in the circuit decay to 37% of its maximum I0 value, 37%. Okay. And the decaying rate or growth rate depends on the time constant. Higher the value of the time constant, the rate of the decay or both will be slower. With increasing of the time constant means the decay will be slow, and also with increasing of the time constant, the rate of the growth of the current in the circuit will be also slower. And the time constant in the circuit depend on the value of the R. With increasing the inductance of the inductor, and the time constant is increases, and also with increasing the resistance, the time constant will be increases. With increasing the resistance, the time constant will be smaller, but with increasing the inductance in the circuit, the time constant will be smaller. Okay. For higher value of t time constant, the slowly decay slowly, so higher value with increasing r decay will be slower. Okay, and for smaller value of L decay very fast. With increasing the time constant, decay of the current will be smaller. Now, what will be the voltage drop at any instant of time during decaying? Here, this is the current. So, the voltage drop across resistance is VR is equal to I into R, and this is equal to R I0 exponential minus R by L t, and VL is equal to L, differentiate it with respect to time, then we get di dt. Okay, di dt, and this is equal to L I0 into minus R by L exponential minus R by L t. So this is the instantaneous voltage drop. If we plot, since the voltage across the resistance is positive, so and with increasing time the voltage decreases exponentially, so this is the variation of the voltage across the resistance, but there is a negative sign in the voltage drop across the inductor, so this will be the variation of the voltage across the inductor. Okay, thank you.